Number 12 has a vase with a given mass moment of inertia spinning and slowing down. We want to determine the torque, the frictional torque that was applied to the vase to slow it down. So imagine it sitting on some sort of spinning table and going pretty fast, 1200 RPMs, and then something causing it to slow down. And that something would be some sort of torque. So we can determine that. Let's write a couple of equations here. We know that torque equals I alpha, where alpha is the angular acceleration, I is the moment of inertia, and this is what's causing the object to slow down. Okay, so we are given I, we want to find the torque, we need to find alpha. Alpha, we're going to assume constant acceleration, so we're going to use this time value right here. So we have to look at our constant angular acceleration equations, okay, and realize that alpha is going to show up in a couple of them. One is, let me write it this way, omega is equal to the initial angular speed plus alpha times time. Acceleration, angular acceleration times time. Okay, this is what's given. This is the 1200 RPM. Okay, slows to a stop is going to be 0, and we're given 16 seconds. So let's convert, as we've always done, our omega 0 into radians per second. So revolutions per minute, 2 pi radians revolution in 1 minute, 60 seconds. Okay, that number comes up to be 1200 times 2 times pi divided by 60. Again, if you haven't watched many of these videos, I intentionally work through all the calculations, both to help you out if there's a difficult calculation and to sort of pace it, that this is the same pace that it would be worked, to not do any things behind the scenes. Okay, so that gives us our omega 0, so we'll write it in here. 0 is 125.7 plus alpha times 16. Okay, so when, 16. So when we multiply or divide through by our radians per second by seconds, that's where we'll get our radians per second squared, which is a unit of acceleration. So alpha looks like it's going to be minus previous number divided by 16. 7.854 radians per second squared. Oops, not sure where that came in. Where my alpha went over here, but there should have been an alpha there. Okay, so now we can calculate the torque. I'm going to write in units here just to talk about how those work out. Kilogram meter squared. Okay, and our alpha. Let's get this out of the way a little bit. And our alpha of, we're just minus 7.854 radians per second squared. Okay, and then recall that a Newton is the same as a kilogram, mass times acceleration, meter per second squared. Okay, so we've shown this before, but just to reiterate, the kilograms show up on the top and the bottom. Okay, second squared on the top is in the denominator. Second squared on the bottom is in the denominator, so those second squareds will cancel out. Radians are unitless. When we start combining things, we're left with meters squared over meters, so one of those meters will cancel out. So we're left with units of Newton meters, which is indeed torque. Okay, so that's going to give us a value of the previous number times our moment of inertia, 0.157. So Newton meters. We weren't specific whether we want a magnitude or some sort of magnitude and direction, so either the positive or negative value here would have been fine.